So welcome to another Advanced Higher Chemistry video. We're still looking at transition metal complexes, but instead of the names of the complexes, we're going to look at what's going on with the electrons and how, when a transition metal goes from being an ion to being involved in a complex, this changes the electron configuration, particularly in relation to the d orbital electrons. So transition metals are characterized by having their d orbitals be their outermost filled orbitals. And in advanced higher, you're typically only going to be looking at the first row transition metals, which involve the 3 d orbitals. When a transition metal exists as an ion on its own, what we would call a free ion, all 5 of those d orbitals are degenerate, meaning they have the same energy. As soon as you bring ligands around a transition metal complex, you are bringing electrons around an atom, which is not energetically favourable. So as soon as you form a complex, you actually cause the energy levels, the energy level of all the orbitals to increase slightly. But it's not even. This diagram as it stands in the middle is just the average effect. In fact, as soon as you form a transition metal complex, you are changing the energy levels of the different d orbitals in different ways. We have 2 orbitals that go very, very, very high in energy, and we have 3 orbitals that only go a little bit higher in energy compared to the free ion. The reason for this is because if you remember the d orbitals, 3 of the d orbitals, when you draw the cross shape, that cross points between the x, y and z axis. Then there's 2 d orbitals which point directly along the x and y orbitals. That's your x-shaped one, or cross-shaped one, points on the x and y axis. And then that weird orbital, the one that's a peanut with a donut around the middle, it points along the z-axis. Now, when a transition metal complex forms, the ligands are located on the x, y, and z axis. And so any orbital that's also on that axis is going to experience a little bit of repulsion from the ligand, and therefore is going to go much higher in energy. The orbitals that don't point directly at these ligands on the x, y, and z axis are not going to go as high in energy. So that's why we have the 2 orbitals that point directly towards the ligands going really high in energy, and 3 not so high in energy. But as long as you know that the pattern splits into 3 at the bottom and 2 at the top, that's the important pattern. Now, why does this happen? Well, it is because, as I've just explained, the d orbitals in an octahedral complex, some of them will point directly at the ligands, and any of those orbitals will experience, the ones that are pointing directly at the ligands will experience a much greater repulsion from the electrons in the dative cobonds, which makes those orbitals higher in energy. The orbitals that are not pointing directly at the ligands do not get as high a repulsion, so will be much lower down. So you get these 2 levels. Now, this splitting between the 2 at the top and the 3 at the bottom is going to be affected by what the ligands are, because some ligands will have much more of an effect than other ligands. So for example, halides, so that's chloride, fluoride, bromide, iodide, they actually don't cause as big a gap. However, as we change the ligands, we go to water, the gap between the 2 at the top and the 3 at the bottom gets bigger. Ammonia, even bigger, and then something like cyanide has a really, really, really high gap between them. And this affects some of the properties that we see within transition metals. So the ligands change this energy gap. Ones bonding through halogens are small gaps. Ones that bond through oxygen, such as water and hydroxide, would be next, smallest. Then anything bonding through nitrogen is the second highest, and then anything bonding through carbon tends to be the highest. So carbonyl, that carbon monoxide one, and cyanide tend to be the highest ones. And we call this energy gap, we just call it delta, a capital delta, so a triangle. Now this has an impact when it comes to putting electrons into the d orbitals of transition metal complexes. Remember, the Aufbau principle states that we always put electrons in the lowest energy orbitals first. So when you're filling the first 3 electrons into a transition metal complex, a transition metal that is part of a complex, they're always going to go into the 3 orbitals at the bottom. However, when you get to the 4th electron, you have a bit of a dilemma, because it has an option. It could pair up in one of the already filled orbitals. There's 3 orbitals at the bottom, they're degenerate, they've all been filled singly. Next electron could start pairing up. Or it could actually go into one of the orbitals that's higher in energy and avoid having to pair up, because remember, electrons don't want to pair up if they can avoid it. So this 4th electron dilemma as to what happens is going to be affected by the size of the energy gap, which is determined by the size of the ligand. So if you've got a small energy gap, such as the case you would have if you had water ligands or halide ligands, the unwanted pairing of electrons is going to be comparable to the energy difference between the 2 orbitals at the top and the 3 at the bottom. So what happens is that 4th electron goes into a brand new orbital. No pairing, which kind of goes against the Aufbau principle. Now, if you've got a really large energy gap between the 3 at the bottom and the 2 at the top, the difference in energy is going to be bigger than the unwanted repulsion of putting 2 electrons in the same orbital. So what happens, in order to have the lowest energy, more stable transition metal, you get pairing. So if you've got a large energy gap, you end up pairing up electrons. And if you've got a small energy gap, you end up using Hund's rule over the Aufbau principle, putting them in individual orbitals. And what this can create is different properties for the transition metals. So see, if this was the same transition metal and we've got water, we can see that we've got 4 electrons all pointing the same direction. We would call this one a high spin version. And the one on the right, well, we've only got 2 pointing in the same direction. So that's lower spin. And this can affect properties such as magnetism. It can affect things such as color, which is what we will be looking at in our next video. How this energy gap and how color arises within transition metal complexes. But from this video, the take-home message is, as soon as a transition metal ion forms as part of a complex, the d orbitals are no longer degenerate. There are 2 higher in energy and 3 lower in energy. And the rules for how you fill those orbitals depends on the size of the energy gap between the 2 at the top and the 2 at the bottom. The bigger the gap, the more likely it is that you will get pairing up of electrons. The smaller the gap, the more likely it is that you will actually start to fill electrons into the higher energy orbitals before pairing up.